We want to find all these zeros or roots of the given degree 4 polynomial function. Because it's degree 4, we can expect 4 complex zeros as long as we count multiplicity, meaning we count possible double zeros and so on. To do this, we first want to find the rational zeros of the function, and we're often asked to make a list of possible rational zeros of the function. Well, the possible rational zeros will be the ratio of the factors of the constant term, in this case negative 40, to the factors of the leading coefficient, which in this case is just positive 1. So we're going to start by listing the factors of negative 40, the factors of positive 1, and then we'll find the possible ratios formed using these factors. The factors are going to be the integers that divide evenly into, in this case, negative 40 and positive 1. So the factors of negative 40 would be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 8, plus or minus 10, plus or minus 20, and plus or minus 40. These are all the numbers that would divide evenly into negative 40. And of course the factors of positive 1 are just plus or minus 1. And because the factors of positive 1 are just plus or minus 1, when we form the ratio of these two, or the factors of negative 40 over the factors of positive 1, notice how the possible rational zeros would just be the factors of negative 40. At this point, we could substitute these x values into the function to determine which of these make the function equal to 0, but this trial and error method would take a lot of time, so what I like to do is take a look at the graph of the function. Remember, our goal is to find the x values that make the function equal to 0, or the x values where y would be equal to 0. So graphically, the real zeros of this function would be the x-intercepts of its graph. So let's take a look at the graph and analyze it. Here's the graph of our degree 4 polynomial. Notice how it has two x-intercepts, which means it has two real zeros, and luckily they're also rational. We have an x-intercept here of negative 4 and an x-intercept here of positive 1. That means two of our zeros of the function are negative 4 and positive 1. This also tells us the other two zeros would have to be complex zeros. So again, because of the graph, we know that two of the zeros are x equals negative 4 and x equals positive 1. Notice how both of these are in the list of possible rational zeros. More importantly, this also helps us factor the original polynomial function. If x equals negative 4 is a zero of the function, then x plus 4 would have to be a factor. And if x equals 1 is a zero, then x minus 1 would also have to be a factor of the original polynomial function. So now we know that f of x must have a factor of x plus 4 and a factor of x minus 1. Because we have a degree 4 polynomial function, and both of these factors are degree 1, this would leave us with one degree 2 factor. So to find this degree 2 factor, we can divide the original polynomial by x plus 4 and x minus 1, or if we want to use synthetic division, we can perform synthetic division with negative 4 and positive 1. Let's go ahead and use synthetic division. Let's start by using negative 4, and then we're going to list the coefficients of the original polynomial function, so 1, negative 3, negative 12, 54, and negative 40. To start, we bring down the 1, and we start multiplying by negative 4. 1 times negative 4 is negative 4. And add, this is negative 7. Negative 7 times negative 4 is positive 28. We add, this would be 16. 16 times negative 4 is negative 64. We add. Negative 10 times negative 4 is positive 40. This is good. We have a remainder of 0. This represents the degree 3 quotient when dividing by x plus 4. But since x minus 1 is also a factor of our original function, it must also be a factor of this reduced polynomial. So now we're going to perform synthetic division with 1 using these coefficients, which again represent the quotient when dividing by x plus 4. So again, we're going to bring down the 1 and repeat synthetic division. 1 times 1 is 1. Add, this is negative 6. Times 1 is negative 6. Add, this is 10. 1 times 10 is 10, and our remainder is 0. So because we started with a degree 4 polynomial, divided by a degree 1 polynomial, and then another degree 1 polynomial, these coefficients represent our degree 2 factor of the original polynomial function. So this factor here is 1x squared minus 6x plus 10, or just x squared minus 6x plus 10. And again, remember, our goal here is to find the values of x that make this function equal to 0. We already found the two zeros from these two factors. Now we need to find the zeros from this quadratic factor. So let's go ahead and do that on the next slide. So now we want to solve x squared minus 6x plus 10 equals 0. This does not factor. There are no factors of 10 that add to negative 6. So we'll have to apply the quadratic formula, where a is equal to 1, b is equal to negative 6, and c is equal to positive 10. If needed, here's the quadratic formula. Let's go ahead and perform the substitutions. We have x equals negative 6 plus or minus the square root of b squared, it's negative 6 squared, minus 4ac, where a is 1 and c is 10, all over 2 times a, or 2 times 1. So this becomes positive 6 plus or minus the square root of, here we have positive 36 minus 40, that's going to be negative 4, all over 2. To continue simplifying, we have 6 plus or minus, well, the square root of negative 4 is going to be imaginary. The square root of negative 4 is negative 1 times 4. Square root of negative 1 is I. Square root of 4 is 2. So we have 6 plus or minus 2i all over 2. And again, we need to be careful when simplifying here. We cannot simplify just the 6 and the 2 here, because we cannot simplify across addition or subtraction. My suggestion is to break this up into two fractions. We have 6 over 2 plus or minus 2i over 2, which would just give us 3 plus or minus I. These are our two remaining zeros, and again, notice how we have two complex zeros. So let's go back to the first slide. We found negative 4 and positive 1 as two zeros, and the other two are x equals 3 plus I and x equals 3 minus I. These would be the four zeros of the original degree 4 polynomial function. Okay, I hope you found this helpful.